Hi everyone. Thank you for being with me again today as I bring you another presentation on Nash Translation 200. Today's topic will be regarding sensitivity analysis with Nastran. In this presentation, expect to go over the following. We are going to go over what a sensitivity coefficient is and how does this relate to plain old calculus. I'm going to demonstrate this with a very simple structural example. I'll then go over the different types of sensitivities you may be interested in. And then throughout all of this, I'll discuss what the procedure is for Nastran. How do you convert a PDF file? What statements do you need and all that good stuff. And as always, if you have any questions or comments, I will have the chat or QA window open to the right-hand side of the video. So if you have any questions, feel free to leave me a comment there. Also, if time permits, at the end of the presentation, I will stick around for a few minutes and you're welcome to ask me any questions after that. Let's go ahead and continue the presentation. This is session 4 out of a 4-part session. All of these sessions are now available on YouTube. I stream all of these on YouTube Live, just in case anyone's wondering. The first one I hosted at the beginning of the month was Optimization Basics with Nash Translation 200. This is a very introductory presentation to optimization. I recommend watching this if you're completely new to Nash Translation 200. These two presentations were more elaborate or more advanced presentations regarding Nash Translation 200. I discuss various examples relevant to the automotive or aerospace sectors. And then this last one is sensitivity calculation with Nash Translation 200. These recordings will be available for today. I will switch over to redoing these presentations again in the coming month. So you'll find new dates here, and here on my YouTube channel. One thing you'll see me use often throughout the presentation is the Nash Translation 200 web app. This is a web application that will let you take an existing Solution 100 PDF file. It will let you create your design model, your variables, your objective, and your constraints, and it will convert it to Solution 200, which is the optimization solution sequence in Nastran. Just in case you're looking for more training on Nash Translation 200, if you want access to the web app, if you want guidance on an optimization project of your own, I am here ready to support you. My email address is here, christian@theengineeringlab.com. And now let's go ahead and move on to our first topic. What is a sensitivity? Let me start with some very simple examples. Here I have this function f is equal to x1 squared plus x2 squared. On the right, I have the f function plotted for you, just so you can visually see what's going on. I also have these two constraint equations, g1 and g2. And then here my design variables are x1 and x2. And we're starting at the starting point of 3, 4. This is almost the optimization problem statement, just in case you're familiar with this. The reason I'm using these examples is because we've all seen examples like this in calculus. We perform gradients, we've calculated partial derivatives in calculus, and this is essentially what a sensitivity coefficient is. It's a partial derivative of a function with respect to a design variable. So here is an example. If we wanted to know what the sensitivity was of x1, it would be the partial derivative of f with respect to x1, and so on and so on. I could do the same for g1 and g2. So that in a nutshell is what sensitivity is. It's a calculation of partial derivatives. Here on the right, I've gone ahead and calculated some of the partial derivatives or sensitivities of these equations on the left. Here I've calculated the partial derivative of f with respect to x1. Here I have 2 times x1, I plug in 3, 4, and I get a gradient or sensitivity of 6. Here I do the same for g1 with respect to x1, I get 2x1 and 6, and do the same for the other partial derivatives here. The reason I'm doing this is because I've already taken time to perform a sensitivity calculation with Nastran for this example. Here again, let me go and show you this plot. Sensitivity, again, is nothing more than finding the partial derivatives of a particular point. For this example, we found the gradient at 3, 4, which would be this orange point that you see me point with the mouse cursor. And let's go ahead and see what Nastran calculated as the partial derivatives. So here is the F06 file of this example. This example I've already done in the past. I've performed the optimization. And here in the F06 file, there's a section called Design Sensitivity Matrix Output, where you have the listed sensitivities for your optimization. Let's go ahead and go back to the presentation and discuss how to read this text. Here on the right is the output, and let me zoom in a little here, and let me discuss what we have. The partial derivatives for each function are separated by these dotted lines. So this section are the partial derivatives of f, partial derivatives of g1, and partial derivatives of g2. In the first column, if you will, and here I'm circling the first column, you have the actual value of f at the initial point. Here, if you plug in 3, 4 to the original function f, you get a value of 25. The F06 file will report this value of 25, and you can see that here. This next section for the next function, if you will, g1, reports a value of 13. If you plug in 3 and 4 to g1, you get 13. And the same thing for the last function, g2. Nastran is reporting the same g2 value at 3, 4. Next, in the following columns, this is column 1 and column 2. In column 2, it could be column 1 for you. This is where you have the actual partial derivative or sensitivity outputted for you. Here, Nastran is reporting a partial derivative or sensitivity coefficient of 5.99, which is close to 6. Here, the actual partial derivative of f with respect to x1 at 3, 4 is 6. And you can see that the other sensitivity coefficients are given here for f with respect to x2, g1 with respect to x1, g1 with respect to x2, and so on and so on. So that's a glimpse as to what sensitivity is. It's calculating the gradients or partial derivatives at a point. I went through how to look at the F06 file and make sense of the output. I know initially it might be a little complex to understand that, but hopefully the last diagram made sense. And now let's move on to an actual structural example. Let me jump out of here and jump to Patron. So here I have a cantilever plate. It's fixed on one end and free on the other end. Let's go ahead and post the first mode shape. We've performed a normal modes analysis on this cantilever plate. Here I'm just showing you some of the mode shapes that you'll find throughout this example, just so you become familiar with this example. One thing I want to make apparent about this example, the thickness distribution. Each strip, if you will have a different thickness. Let me just turn all of these on. In strip 1, which is the fixed end, you'll have the smallest thickness, and you can see the thickness increases as you get towards the free end of the cantilever plate. So again, there are 10 thicknesses here, strip 1, strip 2, so on and so on, until you get to strip 10 at the very end. So let's go back to the PowerPoint and discuss what we defining as our optimization problem statement. Our design variables. We are going to assign a design variable for each thickness. So this will be x1, thickness 2 will be x2, x3, x4, all the way to x10. And our design objective is to minimize the weight. Before, our objective function was x1 squared plus x2 squared. Here, our new f, or objective function, is the weight function. Our design constraints. Before we had arbitrary, or rather custom equations we created for G1 and G2. Here, our G1 and G2 functions are the natural frequencies for mode 1 and mode 2. And keep in mind, we're doing nothing different from before. We're defining our objective function, f. We're defining our constraint functions, G1 and G2. We've defined our variables x1 through x10. When we perform our sensitivity calculation, we're doing nothing different. We are performing the partial derivative of f with respect to one of these design variables. And the same is true for G1 and G2, our design constraints. I have to get a little technical into the Nastran terminology, so I'll do that now. DSvar and dvpro1. And these are bulk data entries that you'll find that are created when you create your Nastran design model. So let me go ahead and open an example. Here in this section, I have my design variables created in DSvar. You'll also have a dvpro1 included in your BDF file. The DSvar entry is what actually specifies your design variable. For example, for the first strip, this is being assigned a P shell entry with a thickness parameter of T1. We then create an entry for the design variable as design variable x1. These two by themselves, a DSvar and a P shell, are not connected yet. You need something to relate the design variable to the parameter. And this is where dvpro1 entry comes into play. Now let me see if I can find an actual example here where I have a DSvar and a dvpro1. So here is an example. I have a lot of dvpro1 statements. This dvpro1 statement is associated to this DSvar entry. Both of these statements combined will link the DSvar entry to the P shell T1 entry through the dvpro1 entry. Now, how are these two connected? One, on the DSvar entry, it will specify the original thickness value of strip 1. The first strip has a thickness of 0.01 meters. So that's here in the DSvar entry. You can see 0.01 meters displayed there. C1 is a constant. Here, it's currently set to a constant of 1. And now the question is, how do these two entries combine to give you the P shell T1 parameter? Memorize this expression for the next few slides. To get the parameter thickness, it will take x1 multiplied by the constant, and then that will give you your thickness. So here I have 0.01 times 1 will give me a thickness of 0.01 meters. During the optimization, the optimizer will vary the entry for x1. So for example, if the design variable becomes 0.02, it would be 0.02 times 1 will equal the thickness of the model here as being 0.02. The constant remains unchanged. So again, the design variable or the DSvar entry is what actually defines the design variable. The dvpro1 is what relates the DSvar entry to the P shell parameter here of thickness. There are various types of sensitivities out there. The first one I'm going to demonstrate is how to create your absolute sensitivities. After that, I'll go ahead and discuss how to create your normalized sensitivities, and then I'll discuss the last type, which is the normalized or relative sensitivities. For the first two sensitivities, you can use the Nash Translation 200 web app to generate these sensitivities. The last type will require some additional work. Now let's go over the procedure before we do this quick tutorial. Number one, create your optimization design model as you would before. Create your design variables, create your objective, and your constraints. Again, your design variables would be your x1s, your x2s, and so on and so on. Your objective would be your f function. Your design constraints would be your g functions. Again, sensitivity calculation is nothing more than finding the partial derivatives of your f objective functions or g constraint functions. To prompt Nastran to perform the optimization, you have to include this statement. This line is included here. This is a statement you can use in your example. And DScreen, this is another statement we have to use, and I'll make a mention of what this is in a moment. Let's go ahead and go through the exercise now. I'm assuming you've started from this standpoint. You've already created your BDF file from your pre-post processor. Here in this example, I'm using Patran. Let's go ahead and go to my desktop and create a new folder called sensitivity calculation. In this folder, I want to copy, or maybe not copy anything there yet. This folder will contain all the files I need to perform the sensitivity analysis, so that's why I created it now. Look for your BDF file, the BDF file that was created by your pre-post processor. This file is currently configured to perform a solution 103 or normal modes analysis. We now have to go through the process of converting all of these to solution 200. So let's go through the process of that. The first thing you'll need is the Nastran Solution 200 web app. This web app is available for free, so if you want access, feel free to email me with your request, and I will definitely work with you on that. To start off with, let's go ahead and copy all of the text in this BDF file, and let's paste it here in the box. When we click Identify Design Properties, it will inspect the entire BDF file, and it will identify all the parameters that can be set as design variables. Here, the thicknesses can be set as design variables. The Young's modulus, the Poisson ratio, and the density can be set as design variables. Here, I'm just interested in setting the thicknesses as design variables. So I can simply click one by one. If you have a lot of design variables, you can use the faster option here. And let's go ahead and click on this Create button here. Let me close that, and let's go ahead and inspect our design variables. We have x1, x2, all the way to x10, and everything looks good here. So now let's move on to creating our objective. When you specify your objective, you don't have to type in a special function for this. Nastran already comes in with built-in objective functions, if you will. Here, for example, is the weight function, and I'll go ahead and simply select the plus icon to set that function or response type as a weight objective. Of course, I want to minimize this. That's probably not necessary for a sensitivity calculation, but I'll set it anyways. And now for constraints. This is where we have to specify the frequency as a constraint function. So we'll go ahead and select frequency once and twice. We'll set this to mode 1 and mode 2. And then for our lower bounds, let me go ahead and see what our lower bounds were. I think it was 5 and 120 hertz. This should be flipped now that I think about it. 5.0 and 120.0. Keep in mind that as we work with the web app, here on the right, you get a preview of your BDF output. The application's it's maintaining, it's managing, it's automatically creating these entries for you. So all you have to do is focus on just here the table configuring everything. We've created the constraint functions. Now we have to create a constraint group. So we can click on Add All Constraints to Group, and we can assign this to all subcases. Now let's go ahead and look at the exporter. Here on the right is my original BDF file. That was a solution 103 BDF file. On the left, it's now converted it to solution 200. It's included the analysis type, the objective, the constraints, and a pointer to the design model PDF file, which would be here on the right. Here I have all the statements for my design variables. I have statements for the objective function and the constraints here on the right. So this looks all good. Let me go ahead and now download this to my desktop. So I can click on download here and download here. And here are my new 2 PDF files. I can copy these and go to my original directory where I will perform the sensitivity calculation. But we're not done just yet. We have to augment this file with 2 statements. The first statement will prompt Nastran to perform the sensitivity analysis. Right now, in its current state, if we were to run this in Nastran, it would try to perform an optimization, but that's not what we want. So let's go ahead and add this statement under the D sub statement. So we'll go ahead and paste that. And we also have to include one other statement, the DScreen Statement. And let me go ahead and take time right now to explain what this is. Or rather, let me go ahead and run the optimization or the sensitivity calculation. And then I'll explain what the DScreen Statement is. So let's go ahead and start Nastran. And we'll go ahead and navigate to this folder and select the model PDF file. And we'll go ahead and prompt Nastran to create our sensitivity calculation. Let me explain what the DScreen statement is. When you perform your optimization and you have dozens of constraints, say for example you're dealing with a stress constraint and you have hundreds, thousands of elements, that could potentially be millions of constraints that are going to be tracked by Nastran. One efficient method Nastran has of handling all of the constraints is by screening the constraints. So for example, if a lot of the constraints are far from being violated, Nastran will essentially ignore those constraints and will only focus and retain critical constraints. So there's sort of a threshold. If the constraint meets a certain threshold, Nastran will consider those constraints while ignoring everything else. During the sensitivity calculation, it uses same screening to calculate the sensitivities. Without the DScreen statement, you could potentially be leaving out constraint values and you could be leaving out sensitivity coefficients. By saying DScreen, it's saying that for the frequency response type, which is our frequency constraint, retain any constraints that have a normalized constraint value greater than negative 10,000 and keep up to 100,000 constraints. Since this example has a small number of constraints, this threshold configuration is more than enough for us. In many cases, this might be enough for you. If you were dealing with stress constraints and you want to calculate the stress coefficients, this FREQ would be stress instead. If you have any questions on how to manipulate the DScreen statement, again, I'm here to support you. Feel free to send me an email. I'd be more than glad to get back to you with that. And now let's go ahead and open the F06 file after our sensitivity calculation. So here, there will be a lot of information, but fortunately, if you scroll to the very bottom and move up a little, this is where you'll find your output. Design sensitivity, matrix output, response sensitivity coefficients. Let's go ahead and go back to my PowerPoint, and now I can discuss how to interpret these results. So here, I've already gone ahead and pasted an image in the PowerPoint so I can describe what's going on here. Again, this first row is for the objective function, our weight. This second row is for our second constraint function. This third row is for our second constraint function. Here we have the response value. So what is the weight for the given initial design? What is the first natural frequency for the first given design and the second natural frequency? Here we have 4.7 and 8.0 hertz. This should definitely be the value that you see in, say, your pre-bus processor. Here I have the same natural frequencies of 4.7 and 80, and that's exactly what I have here in the PowerPoint. This next column is where you start to have your design sensitivity coefficients reported. Here is the partial derivative of f1 with respect to x1, and the value is 67.5. And you have the other various coefficients. Here in the bottom, I have G2, or the partial G2 with respect to x10, and that would be negative 78.24. So this table is very straightforward to understand. That, in a very brief way, is how to perform your sensitivity analysis. This is known as the absolute sensitivities. In a moment, I'll describe what the difference is. Our next step is to create our normalized sensitivities. So now let's go through the process of that. Again, remember that when you specify a design variable, it's the combination of a desvar and a dvpro1 entry. The desvar entry is what defines your actual x variable. The dvpro1 is what defines your constant term, C1, and your p-shell, well, that would have your parameter of thickness. This expression is very important. Remember that. Method 1 is the method we just used to calculate our absolute coefficient. Again, the desvar entry has the initial thickness of the p-shell T1. It has the initial thickness of 0.01 meters. The constant term is 1. If you were to plug these two values into this expression, you get a thickness of 0.01. Now let's flip the assignment. Instead of x1 being equal to 0.01, and instead of z1 equal to 1.0, let's flip these values. Let's now make x1 equal to 1.0, and let's make c1 equal to 0.01. If you still plug in these two values into this expression, you still get the parameter for the thickness. So 1.0 times 0.01 is still giving you 0.01 meters. So this is still a valid way of defining your desvar and your dvpro1. Here in the entries, you know you're using this method when a desvar entry now says 1.0. You'll notice before it said 0.01. And now this entry says p-val, or the original value of the parameter, which is 0.01. This has a big implication because when you calculate your sensitivities, this is what happens. Here on the bottom right, I have an example of what the new sensitivity coefficient will be. Before, with the absolute sensitivity coefficient, we found that the partial of f1 with respect to x1 is 67.5 kilograms per meter. Keep note of the units. With this new method, this is creating your normalized sensitivities with respect to the denominator. So the new sensitivity would be f1 with respect to x1 would be 0.675 kilograms. Now, the way you can get from this coefficient to this coefficient, you would simply multiply your absolute sensitivity times the original parameter value. In this case, it's 0.01. When you do that, that will give you your normalized sensitivity coefficient. So here, I believe I'm just describing the same thing here. Now, let's go ahead and discuss how to calculate normalized sensitivities using the web app. Let me go back here and we'll go through the process right now. So what we'll do is we'll open a new session. I'll copy the entire modded PDF file like before. And I'll paste that here and click on Identify Designable Properties. Before we were clicking on all of these plus icons, there's another option. The DVXRel1 Unity method. Let's go ahead and turn that on. When you check that on, a new column is displayed. What you do now is you click on these plus icons for this column. So 1, 2, 3. Go ahead and do that and get to the bottom. So now I have 10 design variables like before, but you'll notice that the initial values are different from before. The initial values before were the actual parameter values of the thicknesses, 0.01, 0.02, 0.03, and so on and so on. But now they're all 1. Remember that the DV Pro 1 entry is now assuming a different value for C1. It's assuming the original thickness value of 0.01 for this one, 0.02, 0.03, 0.04, and so on and so on. So when you do the multiplication of x1 times C1, you still get the same thickness, so this method is valid. These design variables are now going to produce the normalized sensitivity values. So let's go ahead and do a few things first on our desktop. We'll go ahead and create a duplicate of this folder, and we'll call it sensitivity calculation normalized. And then inside of this folder, we'll go ahead and delete everything but the 2 PDF files. We'll open this design model and we'll delete the old design variables we created. We'll go back to the web app and select and copy these new design variables we created, and we'll paste them here. Now that we have these new design variables, we can perform the sensitivity calculation to get our normalized constraint, sensitivity values, that is. So let me go ahead and navigate to the new folder and click on model and click run. Let me make sure I don't have any memory issues. Yep, let's go ahead and maybe close one of these applications or two. Right now, I experience a memory issue. Since I'm running on a virtual machine, my host machine is already starved of memory, so I have to close one of these resource-intensive applications. And now let's go ahead and open the new F06 file and go to the very bottom and look at our design sensitivity matrix output response coefficients. So here we have our new coefficient of 0.675. This before was being reported as 67.5. And so now let's go back to my PowerPoint and discuss the results. See, I went through that and we were here. Here on the next slide, I've already gone ahead and plotted the sensitivity coefficients for both the absolute sensitivities and the normalized sensitivities. For example, this value for the partial derivative of G1 with respect to X1 was 6.32. If we look back at our F06 file, that would be this value here, 6.3166. I've just gone ahead and taken all these individual sensitivity coefficients and I plotted them using Excel. Here on the left is a plot. You'll notice that the units are different. Here I have kilograms per meter since our F function was in kilograms. Our constraint functions G1 and G2, those were in hertz, so I have that unit here, hertz per meter, and so on and so on. Here by itself, it's hard to come up with any conclusions. Again, what a sensitivity coefficient means, it's a partial derivative or gradient at a specific x1, x2, x3. If we were to increase the design variable, and if we had a positive gradient, that would indicate the value will actually increase. If it was a negative coefficient, that means that you have a negative gradient, so you have a decrease in a value. Here by itself, there's not much to conclude. Some things you can conclude, let me see if I can find something. Here, for example, if you were to increase the thickness of one parameter, that would cause the first natural frequency to go up for mode 1 and mode 2, hence the high blue bars. If you were to increase thickness 10 as an example, that seems to do nothing for the first natural frequency of constraint 1. But here you can see that it will actually reduce the first natural frequency since we have a negative coefficient. Normalized sensitivity coefficients, that's a way of removing one of the units in the sensitivity coefficient. The benefit of this is now you can talk in terms of percent changes, if you will, to a design variable. Here, for example, what's the difference between making a 20% change in thickness 1 versus a 20% change in thickness 10? Here, if I were to change the thickness of by 20% of thickness 1, you can see that there's not much impact to the objective. Whereas if I perform the same 20% change to thickness 10, I can expect an increase if it was positive 20 and a decrease if it was a negative 20. Here, a 20% change or increase in the thickness would impact the first natural frequency of mode 1 or constraint 1 and mode 2 or constraint 2. Now we can consider the situation if we were to increase the thickness 10 parameter by 20%. It could be 30, 40, just to give you an idea of what would happen. Here I can see it will actually reduce the first natural frequency of G1, and it would significantly decrease the value for G2, which is our second natural frequency. Hence we have a negative coefficient here. That still might be a little difficult to really make sense of it. So there's one last type of sensitivity I want to outline, and that is the normalized relative sensitivity coefficient. Let me go ahead and walk you through how to obtain that. To obtain a normalized relative sensitivity coefficient, you would take your normalized sensitivity value and divide it by the response value. So here, let me go through an example. Here I'm using 6.32. So here we have the last calculation we did, which is our normalized sensitivities. I have a value of 6.32. If you divide this value by the response value of 4.7, you will get 1.3 as an example. And you will repeat the process for the next one. So 0.615 divided by 4.7. That will then give you the next normalized relative sensitivity. The benefit of doing or calculating these normalized relative sensitivities is that your new coefficients will be unitless. So now you can interpret the coefficients in terms of change, if you will, without having to worry too much about units. Here, for example, if I were to change the thickness, increase it by 20%, you can see the big impact it would have on the first natural frequency or the first constraint value. Here, same thing. I can see that it would have a big impact on the second natural frequency. If I were to increase the thickness 10 design variable by 20%, you can see it would actually drop the first natural frequency and the second natural frequency. This is very handy in situations where you want to decide what design variables might be worth looking at during an optimization. Some design variables will influence the objective a lot, some will not. If you modify a design variable, how much of an impact will that have on another constraint or an objective? So it really lets you select which design variables are really critical for the optimization. The last thing you want to do is pick a design variable that has little impact on the objective. So that's why it's worth looking at normalized relative sensitivities. So we're at the end of the presentation. We went through a lot. We went through absolute sensitivities, or rather, we went through what a sensitivity coefficient is. It's the partial derivative of a function with respect to a design variable. Our functions could be an objective function, a constraint function. In this structural example, we went over weight and natural frequencies. Other functions could be displacement, stress, strain, and the list is very extensive. We went through the use of the web app to create our design model. We then did a small modification to prompt Nastran to create our sensitivity coefficients. We went through 3 types of sensitivity coefficients. We went through absolute sensitivities, which retain our units, normalized sensitivities, which is the same sensitivity coefficients, but they've been normalized with respect to the design variable. And then the last type, normalized relative sensitivities, which don't have any units and allow us to really make good comparisons between all the sensitivities. So there you have it. That is sensitivity analysis with Nastran. This is definitely an introduction to the world of optimization with Nash Translation 200. Right now, I would take any questions if you have them. I'll stick around for 5 minutes. Alternatively, if you have a question that comes up later in the future, you can send me an email here at christian@theengineeringlab.com, and I'll definitely send you a response. With that, a big thank you for everyone attending. And like I mentioned earlier, I will have various other YouTube presentations, so definitely come back to the YouTube channel. I'm actually having a new presentation next Wednesday, so you're welcome to attend that. Thank you, everyone, and have a great day.